On February 14, 1990, a spacecraft 3.7 billion miles from Earth did something it had no engineering reason to do. Voyager 1 had already completed its primary mission. Jupiter and Saturn were years behind it. The probe was sailing into the outer darkness. Its instruments pointed forward into interstellar space, and the people responsible for keeping it alive were, by most institutional measures, done with photography. What happened that day was not a planned farewell. It was the resolution of a decade-long argument, a bureaucratic and scientific fight over whether spending the final functional hours of a camera system on nostalgia was worth the very real risk of losing data that could never be recovered. The photographs that resulted are among the most analyzed images in the history of space exploration. One of them, a single frame showing Earth as a fraction of a single pixel, would become one of the most reproduced photographs of the 20th century. But almost none of the discussion around these images addresses what they actually were: a technical gamble, approved reluctantly, executed under serious engineering constraints, and concluded by a decision to permanently destroy the very instruments that took them. The campaign that almost didn't happen. Carl Sagan had been pushing for what mission planners called the family portrait since at least 1981. His argument was not primarily poetic, though he was certainly capable of poetry. It was strategic and observational. Sagan's specific case was this: no camera in the history of the species had ever been positioned far enough above the plane of the solar system to see multiple planets simultaneously in a single frame of reference. The geometry would never exist again. Voyager 1's trajectory, shaped by the gravitational assists it had used to reach Saturn, had thrown it upward, out of the ecliptic plane, at an angle that no future mission was designed to replicate. From 40 astronomical units out, 40 times the distance between Earth and the Sun, and elevated above the orbital plane, the spacecraft had a perspective that was, in the most literal sense, unrepeatable. The resistance he encountered was institutional rather than personal. NASA's Jet Propulsion Laboratory managed Voyager's resources carefully, and by 1990, the spacecraft's power was declining. Every instrument running drew from the same shrinking nuclear battery. The cameras were not just an inconvenience. They were a liability. The imaging system required warm-up time, commanded attention from the onboard computers, and introduced risk of data corruption in a communications pipeline already stretched across billions of miles. The scientists responsible for fields like plasma wave detection and magnetometry had legitimate competing claims on that bandwidth. There was also the question of what the photographs would actually show. At that distance, planets would not look like planets. They would look like noise. The argument against the family portrait was, at its core, an argument that you would spend real engineering resources to produce scientifically useless images. Sagan's counter was that scientific uselessness was not the only form of value a space program could generate. He eventually won. The formal approval came in 1989, and JPL engineers began the genuinely difficult work of preparing a camera system that had not taken an image in nearly 4 years. Restarting a dead-eye Voyager, 1's imaging system was built around a Vidicon tube, an analog television camera technology that translates optical information into an electrical signal by scanning a photosensitive surface with an electron beam. Vidicon systems are mechanically and thermally sensitive. After years of dormancy in the radiation environment of deep space, the tube's photosensitive surface required a careful warm-up sequence before it could produce usable data. Rush that process, and you risk permanent damage to the surface. Do it correctly, and you get, maybe, one reliable window of operation. The onboard computers presented a separate challenge. Voyager 1's flight data system ran on memory that had been configured for the probe's active science mission. To execute the family portrait, engineers at JPL had to uplink new software commands to rewrite portions of that memory. A process that took weeks, given the 5.5-hour one-way communication delay at that distance. A command sent from Earth would not arrive for nearly 6 hours. Any error in that command sequence would not be discovered for another 6 hours when the error response came back. There was no real-time interaction. There was only careful planning and waiting. The pointing accuracy required was also extraordinary. To photograph Earth, engineers needed to know where Earth would be, not where it was, but where it would be when the light they were calculating would actually arrive at the camera. At 3.7 billion miles, the angular diameter of Earth, as seen from Voyager 1, was approximately 1/12 of a pixel. The camera would have to be aimed at a calculated position in space and expose for a specific duration to catch a point source of reflected sunlight against the background of the solar system. The timing precision required for this kind of work, executed over a communication link measured in hours, represents one of the more underappreciated feats in the history of robotic spaceflight. What the camera saw, the family portrait mosaic, consisted of 60 frames taken over 3 hours on February 14, 1990. Not all of them contained planets. Most were deep space, darkness that confirmed the distances involved. 6 frames contained what the imaging team was looking for. Saturn appeared as a small crescent, its rings caught at a severe angle that compressed them into a thin, bright line. At 40 astronomical units, the gas giant that had dominated Voyager 1's closest approach images just years earlier was reduced to geometry. The image is technically clean. Saturn was the easiest target because of its size and the reflectivity of its ring system. It appears in the mosaic as a pale shape against black. Jupiter was also captured as a crescent. At that distance and phase angle, only a sliver of the giant planet was illuminated from Voyager's perspective. Jupiter's clouds, its bands, the great red spot, all of that was invisible. What the camera recorded was a bright arc, the sun-facing limb of the largest planet in the solar system, reduced to a comma of light. Uranus and Neptune were pushed to the limits of what the system could record. Both appeared as single bright dots, their disks unresolvable. The interest in these 2 frames is not visual but geometric. They are included in the portrait because they were there to be included, because the geometry permitted it, because no other camera had ever occupied that position. Venus was captured with striking clarity relative to the other planets, appearing as a bright crescent. It is the most visually satisfying of the planetary images, precisely because Venus is highly reflective and was positioned favorably in the mosaic. And then there was Earth, 0.12 pixels. Earth occupied 0.12 pixels in the raw data from Voyager 1's camera. That number is not rhetorical. It is a calculation derived from the angular diameter of Earth, as seen from 3.7 billion miles, divided against the resolution of the Vidicon imaging system. The planet did not fill a pixel. It occupied a fraction of one, and that fraction was bright enough against the background darkness to register as signal rather than noise. The image you have seen, the one with the blue dot suspended in a column of amber light, is not a single exposure. It is a color composite assembled from 3 separate images taken through 3 different filters: violet, blue, and green. The process of combining these frames is how color information is reconstructed from a camera system that did not capture color in a single shot. The blue tone associated with Earth in the final image comes from the filter combination and the reflectivity characteristics of Earth's atmosphere and oceans at those wavelengths. The column of light crossing the image, the sunbeam effect that makes the dot appear to float in a ray of illumination, is a lens artifact. Voyager 1 was photographing the inner solar system from a position close to the line between Earth and the Sun. The scattered light from the Sun entering the camera's optics created a diffraction artifact, a bright band that has nothing to do with the subject of the photograph. The Earth happened to fall within that band. The result is an accidental composition, the most famous accident in astronomical photography. Had the scattered light not appeared, the image would still be scientifically identical. Earth would still be 0.12 pixels. The engineering fact of the photograph would be the same. But the artifact transformed the image from a data point into something that looked, to human eyes, like meaning. The missing planets. 3 planets are absent from the family portrait, and the reasons are specific. Mars was excluded because its position relative to the Sun, as seen from Voyager's location, placed it too close to the solar glare. The scattered light that created the sunbeam in Earth's photograph would have completely overwhelmed any reflected signal from Mars. The decision was not difficult. Photographing Mars from that geometry was not physically viable. Mercury presented a more severe version of the same problem. Mercury orbits so close to the Sun that from 40 astronomical units, it was essentially inside the solar disk from an optical standpoint. No exposure setting available to the imaging team could have captured Mercury without destroying the sensor. Pluto, still classified as a planet in 1990, was simply too small and too dark. Even without the glare problem, Pluto's reflectivity and size at that distance would have placed it below the detection threshold of the Vidicon system. The camera could not have seen it. The absence of Pluto in the family portrait is an engineering limit, not an oversight. The permanent shutdown. After the family portrait was complete, JPL engineers made a decision that remains the defining endpoint of the Voyager 1 imaging story. The cameras were shut down, and the memory that had been reprogrammed to operate them was overwritten with new data. This was not ceremonial. It was thermal and logistical. The camera platform required heating power to prevent its mechanical joints from seizing in the cold of deep space. That heating power, drawn from the same declining nuclear source that powered everything else on the spacecraft, was needed for instruments considered scientifically essential: the magnetometer, the plasma wave detector, the cosmic ray instrument. These sensors were returning data about the boundary between the heliosphere and interstellar space, a region no spacecraft had ever entered. The choice between maintaining the cameras and maintaining those instruments was not philosophically difficult. The memory overwrite was permanent. The software that had been loaded to enable the family portrait, the specific command sequences, the pointing calculations, the exposure parameters, was erased and replaced. There was no archival copy stored aboard the spacecraft. There was no mechanism to restore the imaging capability. From that point forward, Voyager 1 was, in terms of photography, finished. What was lost is worth stating clearly. The camera system was functional. It was not broken, not degraded beyond use, not destroyed by cosmic ray impacts. It was operational hardware that was deliberately placed beyond recovery because the mission's scientific priorities had shifted and the power budget had narrowed to the point where choices had to be made. The cameras are still out there, still attached to the spacecraft, still physically intact in the way that objects in vacuum tend to remain intact. They simply cannot be operated because the software and the power allocation no longer exist to support them. What travels now? As of 2024, Voyager 1 is approximately 24 billion kilometers from Earth, the most distant human-made object in existence, operating in interstellar space beyond the heliopause, the boundary where the sun's influence gives way to the interstellar medium. It is still transmitting. The signal arrives at Earth after more than 22 hours of travel time, weakened to a fraction of a billionth of a watt, and requires the largest antenna arrays humanity has built to detect. The cameras are still aboard. They are traveling through interstellar space at roughly 17 kilometers per second, pointing at nothing, receiving no commands, performing no functions. The Vidicon tube is there, the optical systems are there, the mechanical pointing platform is there. In 40,000 years, the spacecraft will pass within 1.6 light years of a star in the constellation Camelopardalis. The cameras will be with it when it does. The family portrait was not the end of Voyager 1's scientific life. The probe continues to return data that is changing our understanding of the boundary between the solar system and interstellar space. But it was the end of the spacecraft's relationship with visual imaging, with the idea that human beings wanted to see what was out there, not just measure it. The photographs exist because Carl Sagan spent a decade arguing that the view from the outside had value beyond its data content. The cameras are silent now because the engineers who listened to that argument were also right about everything else. The power budget was real, the competing science was real, and every watt spent maintaining a camera that had done its work was a watt not spent on instruments still doing theirs. Both things are true simultaneously. That is perhaps the most scientifically honest thing about the pale blue dot. Not what it shows, but the precise set of trade-offs that made it possible and the precise set of trade-offs that ended it.